Here you go. So I think that number 1 should be 5x minus 2. 5x minus 2. So I did a distributive property with a -4, and then I added the like terms up. That's what I got. So let's just go one by one here. So for number 1, 5x minus 2, is there anything I can explain better, show further, answer a question? It's probably my fault. Like if you're not understanding something, I could probably try to explain it differently, and we could probably get there. So please think of it that way. That's how I think of it. So on number 1, 5x minus 2, what can I do to explain that differently, if needed? For number 1. Okay, so then number 2, I got -42. -42. This is a pretty tough evaluation, right? An order of operations, PEMDAS thing. So I kind of squeezed in a little bit there. So there might be some explaining that I need to do with number 2. Remember, PEMDAS means do the work inside the parentheses first. Once you've cleared all that up, then you do any exponents. Once you've cleared that up, then you're on to multiplication and division. Once you've done that, it's addition and subtraction. The temptation is to read from left to right, isn't it? Just always read from left to right. It's not how we read in math. In math, we read according to PEMDAS. So that might mean from right to left, or middle to out, or over here, and then left to right, or something like that. So you want to be really careful that you evaluate correctly. So how can I differently explain number 2? Anybody want to have a question, see something? I don't know. Okay. While you're pondering that, we'll practice this again tomorrow. I believe we have DMR 15, it would have to be. Right? Yeah, DMR 15 would be on Friday of this one. Okay, so then on to number 3, the graph. So I tried, it's kind of hard. I tried to use colors, but even with colors, it's kind of hard to see. So that's why I drew that little arrow that says, that little triangular area is the answer region. So you've got a vertical line, and then a line with a negative slope, and that other line has a positive slope in the end. There was a trick with division by negatives and to flip the inequality around. There was a lot going on with number 3. A lot going on there. So maybe 2 of the 3 parts made perfect sense to you, but 1 part didn't. I don't know. Thoughts on 3? Anybody want to hear that talked through, explained differently, besides what's just on the screen? Anything?
When I did the shading, I thought it would be where the red is.
Okay.
But how'd you get where the orange?
Sure. Let's see here. So you agree on the lines. You're good with the lines. It's just a question of shading. I'm just trying to think about how I can do this most efficiently. I'll do this. So we already know what the graphs look like. So I'm just going to erase this real quick, and then I'll use like maybe a different shading technique, and let's see if we get anything different. So the first one is that vertical line. X is greater than -2. So I'll do this. And it has to be a dotted line, of course. Let's go with this. So there's that. And this. So now it's dotted. And I think what I'll do is I will shade. Hopefully this will make sense. I'm going to just shade with something like this. I'll just use lines or just like scribbles, probably like you did, right? Mm-hmm. So there's my shading for that one. And then the next one has a y-intercept of 6 and a slope of -1/3. So something like that seem reasonable? Okay. And then the shading on this, so I'm just going to do this in my head. I'm going to test out 0, 0, the thing we always do. So I test out 0, 0 in this red line. I get 0 is less than or equal to 0 plus 6. So is 0 really less than or equal to 6? 0 is less than or equal to 6, right? It's less than. So it fits. So I would shade the 0, 0 side, and it would look something like that. So far I've got that region going on. You can see the overlap in there. And then the other one, the final line, is y is greater than or equal to 3 halves x plus 4. So something like that. I'll extend that a little bit. Okay, so now when I try 0, 0, I get 0 is greater than or equal to 0 plus 4. So also known as 0 is greater than or equal to 4, and that's false. And that might have been where you said true. I'm guessing that had to be it, right? So I think that 0 is not greater than or equal to 4, so I will not shade on the 0, 0 part. I will shade on the other part, so that would be this right there. And so the only part that has all three shadings overlapping is that triangle right there. Ellie, is that a good explanation?
Yeah.
Okay. That also could happen if you forgot to flip your inequality around when you divided by a -2.
Okay.
If you forgot that, then that would make a difference.
Yeah.
That would probably lead you right to the answer you were talking about. So that could be it too. Thanks for asking. Anybody else on number 3? I like this graph better. More colors. Okay. So then finally we get to number 4. I got an answer of 4 root 3. And you can kind of, this one might be the one we need to talk about the most because it's down there at the bottom. You want to talk about this one?
Could you do the whole thing?
Let's do the whole thing. And let me shift where this screen is. So, do you guys remember when we are adding radicals, in order to add radicals, they have to be like radicals? So in other words, all of them have to be like root 5s, or all of them have to be root 7s, or root 10s, or whatever it is. So when you first look at number 4, can you see how someone could be fooled into thinking that none of those radicals are like radicals? So the answer is you can't add them. Can you see why somebody would think that? But you guys are a little better than that, right? You can investigate a little further because maybe you noticed at some point that this square root of 12 and the square root of 27, neither of those is prime. And since neither of those is prime, you can actually simplify them potentially, right? So what I noticed some of you guys doing as I walked around is some of you are just jumping in right here and you're saying 12 is really 4 times 3 and 4 is really 2 times 2. And you said 27 is 3 times 9 and 9 is really 3. You're just doing your factor trees right there. It's not the greatest notation in the world. Like a mathematician is going to say, nah, you need to do better than that. I think I'm okay with that if you can get these prime factors settled. This would be a good place to be. So once you do this, you could write square root of 3 plus 9 times the square root of 2 times 3 minus 5 times the square root of 3 times 3 times 3. And now, if you haven't already, you probably noticed that there's a pair of 2's in the first radical, and then there's a pair of 3's in the second radical. Isn't that what we're looking for? So I see these 2 2's and these 2 3's. Remember that 2 2's on the inside come out as a single 2, and 2 3's on the inside come out as a single 3. Yeah.
What do you do with the 2 extra numbers?
The 9 and the 5?
Well, so you have the 2.
Oh, like the leftover 3's?
The leftover 2 3's.
They just stay inside the radical. They can't come out because they don't have a pair.
So you're canceling out the 3 and the 3 and the
They're being square rooted essentially. Because think of it like this: isn't 2 times 2 4? And what's the square root of 4?
2.
2. So check it out. So this would be square root of 3 plus 9 times, look at the screen, 9 times 2 times the square root of 3. So that 2 in there, that's your square root of 4.
Okay.
And then minus 5 times 3 times the square root of 3. And that 3 that just showed up outside the radical, that's your square root of 9 that you actually did. Okay. So then you get square root of 3. 9 times 2 is 18. And 5 times 3 is 15. So now when you look at these, you realize all these radicals, at first they appeared to not be like radicals, but they actually are like radicals. So you have 1 of them plus 18 of them is 19 of them. 19 of them, take away 15 of them, you end up with 4 of them. So 4 root 3. Uh-oh, doesn't sound very...
I got 18 minus 15.
Oh, so you just missed the fact that this is 1 root 3. And if you have 1 of them...
Why is that 1 root 3?
Oops, let me erase this. How many root 3s are in the green box?
1.
So you could write this as 1 root 3. 1 times root 3. Just like if you see an x, couldn't you rewrite that x as 1 times x? Or frankly, if you saw a 9, couldn't you rewrite that as 1 times 9? So if there's no coefficient on the front, we know that it's a 1. Okay, anything else I can do for you guys on number 4? Okay, very good. Grab your computers. You're going to be doing some work with polynomials through Desmos. So if you would, please go to Desmos and put in that code BX3C5P. I'm going to have you guys do a little exploring with Desmos, and we'll have an exit ticket at the end. Tomorrow, guess what we'll do? We'll work with polynomials again. We'll reinforce all this stuff one more time. Have a good rest of your day.